Hi everyone, welcome to my YouTube channel VLSI Excellence. In this lecture, we are going to cover Verilog STL design and simulation of UART, which is Universal Asynchronous Receiver Transmitter. So before I start this video, I just wanted to let you know that if you are looking for VLSI contents related to static timing analysis or VLSI low power concepts or Verilog concepts, you can consider visiting my YouTube channel, which is youtube.com/VLSI Excellence. So now let's get started. So let's understand few important key points related to UART. So a UART is a digital circuit that sends parallel data through a serial line. So the meaning of this statement is, suppose we have a UART controller. Let's assume that it is UART TX controller. So this TX controller will receive some data in parallel form, and that data might come either from some memory or some or CPU can write the data parallelly into some register of this TX controller, and then this TX controller will send that data serially through its TX line. So basically there are two lines in UART communication protocol. One is UART TX and another one is UART RX. So this is how the UART communication system looks like. We will cover this in more details in the incoming slides. The main purpose of UART is to transmit and receive data serially. Okay, now two UARTs communicate directly in UART communication system. So in UART communication system, we have only two UARTs which are communicating directly to each other. And UART transmits data asynchronously. So if you see here, we only have two lines or two signals between the UART transmitter and receiver, which is UART TX and UART RX. And there is no extra clock signal here between the UART TX and RX. That means the TX controller and the RX controller, which are out of phase and they are not synchronous to each other, right? So that is why, so suppose it is running at clock 1 and it is running at clock 2, and this clock 1 and clock 2 is asynchronous to each other. So one important point here, these two clocks, the frequency of these two clocks can be same. The frequency of these two clocks can be same, but they are not synchronous, because the source to this TX can be different and the source of clock to this RX can be different, and hence the both TX and RX are not running at a common clock, and hence there is no clock signal to synchronize the output bits from the transmitting UART to the sampling of bits by receiving UART. Okay. Now let's understand how the UART communication protocol looks like in a big system. So suppose we have a big system, and in this system there are two subsystems. Let's assume there are two subsystems, subsystem 1 and this is our subsystem 2. So these two subsystems are basically communicating to each other through UART communication protocol. So how their connectivity will look like? So the TX line of the subsystem 1 UART control will get connected to the RX line of subsystem 2 UART controller, and similarly the TX line from the subsystem 2 UART controller will get connected to the RX line of subsystem 1 UART controller. And here, as I said, the UART controller here is receiving the data parallelly, and then it will transmit it serially, and then the UART2 here will basically again convert that serial data into parallel form, which can be again read by CPU or it can be written into memory. So this is how a UART communication system looks like. Now let's understand the UART operating principle. So the transmitter UART basically converts the received parallel data, for example CPU or memory, into serial form. And now the UART transmitter adds start and stop bits to the data packet in transfer. So very important point, as I said here, these two UART TX and UART RX controllers are running at their own clock. The clock is not synchronous to each of the blocks. That means when this TX controller is transmitting the data, this RX control, since this is transmitting the data at clock 1 and this RX will receive that data at clock 2. So they are asynchronous to each other. So there is no guarantee that this data will be get captured at this UART RX controller side. Again, very important point, the frequency of UART clock 1 and UART clock 2 can be same, but they can be asynchronous to each other. So in order to make sure that the UART receiver receives that data correctly, the UART transmitter has to make sure that the UART receiver understands that it is going to send some data. So to do that, the UART transmitter basically appends some extra bits with the actual data, and that bits are called start bit and stop bits. So the UART transmitter, before sending data, it appends extra start and stop bits with the data packet, and then it sends that packet serially to the UART receiver. So as I said, when the UART receiver will receive the start bit, so the start bit is a specific bit. It is not a random bit, it is a specific bit, and the stop bit is also a specific bit. So when the UART, I will cover this in more details in the slides. So when the UART receiver detects the start bit, it will understand that okay, now next the actual data is going to come. So it will start sampling that or reading that data. Now when the receiver UART detects a start bit, it starts to read the incoming bits at a specific frequency known as the baud rate. So this is very important point here. Both UART receiver and UART transmitter, so they have to work at a specific frequency, and that frequency is known as baud rate. The meaning of this statement is the UART transmitter has to send the data at a particular frequency, that is called as baud rate, and the receiver, UART receiver, has to sample the data at a specific frequency, that is also called baud rate. So this is nothing but a baud rate concept where the both UART transmitter and receiver has to work at a specific frequency, and that frequency is known as baud rate. And once the receiver has received the data, it will remove the start bit, the parity bit and the stop bit from the UART data packet, and it will extract the actual data, and that data it will convert into a parallel flow. So baud rate is the measure of the speed of the data transferred, expressed in bits per second. So the UART transmitter will transmit the data at a specific frequency known as baud rate, and both receiver and transmitter has to work or has to basically send the data or receive the data at a particular frequency, that is baud rate. So both TX and RX UART should operate at about the same baud rate. So again, I just wanted to make sure here that they have to operate at a same baud rate or suppose a same frequency, but it doesn't mean that same frequency will guarantee that both the clocks are synchronous to each other. They can be out of phase. So we can only confirm about the synchronicity when there is a common clock signal between transmitter or receiver. And here in UART communication protocol, we know that we do not have a common signal between UART TX and RX. We only have a UART TX line and a UART RX line. Only one master and one slave device can participate in UART serial communication. Now this is the UART data frame actually. So here we have the start bit, and then we have our actual data which we have to send, and then we have one optional bit which is parity bit. So this parity bit, as per the user applications, we can either send a parity bit and we can have that not included, and then we have one or two stop bits. So each UART packet contains one start bit, 5 to 8 data bits depending on the UART, and an optional parity bit and one or two stop bits. So parity bit basically it used for the error detection. For example, parity bit. So if the number of ones in the data, this 5 to 8 bits, the number of ones is even, then the parity bit will be set. if the number of ones is odd, then the parity bit will be 0. So this parity bit is used for the error detection in UART communication system. So as we covered, the UART data frame is considered as a combination of 4 basic components: the start bit, the input data, the parity bit, and the stop bits. Now let's see some advantage of UART communication. So as you see, there are only 2 signals in UART communication, so less number of signals. Then we do not have the clock signals also, and another example is error detection using parity. The disadvantage of UART communication is it is a serial communication. So if it is a serial communication, there will be less throughput. Then there is a limited data frame, 5 to 8 bits data frame. Then again we have to start and stop. If you have to send the continuous data, we have to keep making those UART packets, and then we have to send. So the data is limited by the UART frame, and only one master and slave device is supported in UART communication protocol. Unlike I2C, where we have multiple master and multiple slave, here in UART communication we only have one master and one slave, and both ends should have similar data transfer settings. For example, baud rate. So baud rate, whatever baud rate we set at our UART transmitting side, the same baud rate we have to set at our receiver side. So these are few of the disadvantages of UART communications. And this is the UART data frame format. So if you understand here, and this has to be very much clear to you, that when there is no data communication happening through the UART TX line is held high. Okay, suppose here we have the UART TX and here we have the UART RX. So we are sending the data from TX to RX. So when there is no data transfer is happening, this TX line is held high. Okay, and as soon as the transmitter wants to send the data, it will pull the TX line low, and that is going to be our start bit. So whenever there is a transition from high to low, it is an indication that UART transmitting is going to happen. And then we can send the data bits, and this is optional, our parity bit, and then we have to send the stop bits that will indicate our stop condition. Now here is the block diagram of UART TX controller. So there are basically 2 major components in UART TX controller. One is baud rate generator, and the another one is the control logic for the UART TX communication. So the baud generator will generate a particular baud rate, and then the UART TX controller will basically send the data at that particular baud rate. So if you see the interface signals here, we have the data, parallel data, then this is a TX ready signal. So whenever the transmitter is ready to send the data, this TX ready signal will get accepted and the transmitter will start transmitting the data. Then we have the clock signal and reset signals. So here this is the TX line, this is a serial TX line, and here it also indicates the TX done. So when the 8-bit data is sent or the data packet is sent, the TX done will be high for 1 clock cycle. And here we have the state machine for UART transmitter. So on reset, the UART TX is going to be on idle state, and whenever the TX ready signal is asserted, we are going to start state, which is basically nothing but it will pull the TX line low, and then we are going to the data state, which will basically send the, suppose 8-bit data here, so it will send the 8-bit data, and then we will go to the stop state, where the stop condition, which is nothing but the TX line is high for few clock cycles, and then we will go to idle state. In idle, again, if TX ready is high, we are going to start our new UART frame. So this is how the transmitter will transition through the different states. Here is the UART receiver block diagram. So again, it also has the 2 major block components. One is baud rate generator. So it will again generate a baud rate which is similar to the UART transmitter baud rate, and then this UART RX controller will basically start sampling the UART TX line, and whenever it detects the start bit, it will start sampling the data. So it will receive the data serially, and 1 clock signal and 1 reset signal, and then it will basically convert the data in parallel form, which will basically can be read by CPU or memory. and once the data is received, all 8-bit data is received, the RX done signal will go high for one clock cycle. So here we have the state transition diagram for the UART receiver. So as soon as reset is asserted, we are in the idle state, and when the reset is deasserted and if input RX data is 0, we are going to start condition. So we have the UART TX and the UART RX controller. So this is UART TX transmitter and this is receiver. So this is the TX line, this is the RX line. So the TX line will get connected to the RX line in the UART receiver. So by default this line will be held high. So as soon as this line goes low, that basically indicates that the UART transmitter is going to start a new frame, or it is going to transfer some data. So the line will go low. So the UART receiver is basically sampling this TX line or the RX line of its own, and whenever the RX line goes low, it will go to start state. So whenever the input RX data is 0, that means the start condition has happened. It will go to start state, and from start it will now start reading the 7 or the 8-bit data, and then once the 8-bit data is received, it will go to stop, and from there it will go to idle state, and the stop, in the stop condition it will check if the RX line, its own RX line is high for few clock cycles, and then it will go to idle state. So now let's understand one important concept of oversampling. So as I said, the UART transmitter and receiver has to work at a specific frequency, which is baud rate. Correct. Now I have another concept of oversampling. Okay. So what does that mean? Suppose our UART transmitter is sending data at a baud rate R. Okay. Now oversampling is basically a concept associated with UART receiver. So the UART receiver now can oversample the data at a higher frequency or at a higher baud rate. So if the UART receiver wants to sample the data at a higher baud rate, it has to basically generate a frequency or a baud frequency which is multiple of this transmitter baud frequency or baud rate. So here suppose the oversampling is 16 times, the receiver is going to have 16 times oversampling. So the receiver is now sampling the data at a frequency of or at a baud rate of 16 R. So the physical meaning of this is, suppose the transmitter is sending the data at a baud rate R, but now our receiver is sampling this bit. This is one bit here. So now the receiver is going to sample this bit 16 times. So basically it is oversampling this. In normal condition, when the UART TX and RX baud rate is same, the UART receiver will sample this bit only once. But now this UART receiver is going to sample this bit 16 times, for example, and then it is going to determine if this bit, what is the value of this bit, whether it is 0 or 1. So this kind of concept is basically important when we want to filter out any kind of noise in the UART communication. For example, this is our 1 bit. This is high bit. The UART is sending a high bit, and there is some noise, and this bit will become 0 here for just for few time. It will become 0. So if our UART receiver is sampling at the same baud rate, and if it happened to sample this data at this particular instance only, then instead of 1 it will sample it as 0, right? And it will receive a wrong data. But with oversampling, when it is sampling the data at 16 times, the probability of having a noisy data will get reduced. So that is how we have introduced a concept of oversampling in the UART communication system. So the UART receiver can oversample the data, and it can determine what is the data value, or more specific, the bit value. The oversampling scheme works as follows. So here I have taken one example of 16 time oversampling. So this is this concept is associated with the UART receiver. So the UART receiver will wait until the incoming signal becomes 0. That is what the start condition is. So the UART receiver is basically going to wait or going to sample the RX line until it receives a 0, which is the beginning of the start bit, and then it starts sampling the sampling tick counter. So once it detects 0, it will start its counter. Okay, and when the counter reaches 7, okay, the incoming signal reaches the middle point of the start bit. So important point here, as I told, the UART transmitter is sending the data at a baud rate R, but the receiver is now running at 16 R. So as soon as the receiver receives a 0, it will start the counter, and when the counter reaches to 7, 0 to 7, that is basically nothing but middle of the bit. Suppose this is the bit which transmitter has sent. So now, and this is suppose the start bit. So this is our start bit. So as soon as this has become 0, the UART receiver will start the counter, and when the counter, so now the UART receiver is running at a higher baud rate, 16 times of UART transmitter. So as soon as the RX line becomes 0 or the start condition happens, the UART receiver is going to start its counter, and when the counter reaches 7, that means nothing but the mid position of the start bit, right? So when the counter reaches 7, the incoming signal reaches the middle point of the start bit. Now clear the counter to 0 and restart. Now I will clear the counter, I am going to restart. Now when the counter reaches to 15, that means I have reached middle of the first bit. The incoming signal, when the counter reaches 15, the incoming signal progresses for 1 bit. So the first bit, basically I am at the middle of the first bit. So retrieve its value and shift it into a register and restart the counter. So I will basically now at middle of this point and middle of this bit, I will sample this bit, and again I will restart the counter, and then once it again reaches to middle of the second bit, I will sample this. So if there is a glitch between here, that glitch will be eliminated, or that glitch will not have an effect on our data read. So this is how the oversampling scheme works. So repeat step 3 to retrieve the remaining data bits. So this is how we have to keep on running the counter, clearing the counter, running the counter, and sampling the bits until we receive all the bits. And if there is any parity bit, we have to repeat the step 3 for the parity bit as well as for the stop bit. This is how the oversampling scheme works. So guys, as I said, if you are looking for VLSI contents related to VLSI, Verilog HDL crash course, static timing analysis, interview practice questions, low power VLSI concept theory concepts, low power VLSI design practice or interview questions, or some more digital ASIC design Verilog projects, you can visit the links which I will provide in the description section of this video, and you can visit my YouTube channel and you can find a lot more VLSI related contents there. So now we are going to, now let's walk through the Verilog code of this UART controller, and then we will simulate it and we'll see the results.